So in the previous video set, we took a look at being able to solve these series solutions, and basically we were able to utilize functions that had any sort of radius of convergence. So I think we looked at e functions or natural exponential functions, as well as sine and cosine functions. But what if we have solutions that only exist around certain points? So what we do is we like to use a separate form. And the form that we're going to utilize is this c sub n x minus x naught to the n. So before it was just x to the n. So x naught is going to be the point to where we center the function around that we're going to find. And we're going to utilize all the same techniques that we learned in the previous video series. So the good news is we're really not going to be learning too much new, but we're going to be putting everything together. And we might have a new way of writing the solutions. Remember, because we have a second order differential equation, we are going to have two separate series solutions. So we'll probably have like a y1 and a y2, similar to what we had in the last example. So let's start off with a fairly easy, and when I say fairly easy, there's no such thing as an easy series solution, but with respect to the difficulty of these, we have this x squared plus 1, y double prime minus 6y equals 0, and we're trying to find the solution about the point x naught equals 0. So for our proposed solution, y is going to be the series n equals 0 to infinity, c sub n x minus 0 to the n, which is actually the same series that we used in the previous three examples. So c sub n x to the n. All right, so the good news is for this example, we're going to be using the exact same series. Y prime is going to be the same y prime, and notice that we shifted the index up by 1, so it's n equals 1, c sub n times n times x to the n minus 1. And then finally, y double prime is going to be equal to the series n equals 2 to infinity, c sub n, n minus 1, x to the n minus 2. And we're going to substitute y double prime and y back into the original differential. So we're going to end up with this series. So we're going to say x squared plus 1. Instead of y double prime, it's going to be series n equals 2 to infinity, c sub n, n minus 1, x to the n minus 2, minus 6 of the original series, n equals 0 to infinity, c sub n, x to the n, and that's going to be equal to 0. Now, this is something that we didn't see in the previous previous examples. What happens if we have a binomial expression as our coefficient? I mean, remember when it was a singular monomial expression, we just substituted it into the series and we did some algebra. Well, we're going to do the exact same thing, but we're going to distribute. And we're going to end up with two series, and then, so we're going to get two series out of this distribution, and then we're going to have one additional series. So in fact, we're going to end up with three separate series. All right, so let's just go ahead and do that. So we have x squared series n equals 2 to infinity, c sub n, n minus 1, x to the n minus 2, plus one series n equals 2 to infinity, c sub n, x to the n minus 2, n minus 1. All right, and I didn't do that for any sort of reason to flip those around. I was just writing, and I wrote the x to the n minus 2 first, just because that's the first thing that came to mind. And then finally, we have the minus 6 n equals 0 to infinity, c sub n, x to the n equals 0. So what do? Well, just like we did before, we're going to distribute the x squared back into the first series. There's nothing else to really do after that, so we're going to get series n equals 2 to infinity, c sub n, n minus 1, I'll throw the n right here, x to the n. All right, so notice we have 2 and negative 2, so those are really just going to cancel each other out. plus 1 series, or just n equals 2 to infinity, c sub n x to the n minus 2, n minus 1, and then minus 6 of the original series. So minus series n equals 0 to infinity, c sub n x to the n equals 0. We're going to use the same techniques that we learned before. So what we're going to do is we're going to make all the powers of x look the same. All right? And we're just going to use a change of variable. Now, the only one we really need to change is the second series. All right? So if n equals k in the first series and n equals k in the third series, the only thing we'd have to do is just substitute for n to make it look like k. And we're going to let n equal k plus 2. And the reason we do that is because we can get n plus 2 minus 2, which is just, or k plus 2 minus 2, excuse me, which is just going to turn into k. Now the other thing we have to remember is that n minus 2 is equal to k, because that's going to change the lower bound, just like it did in the other series. So, now we're going to get series k equals 2 to infinity, c sub k, k minus 1, x to the k. Now this is the only series that's truly going to change more than any other one. Now notice we have n minus 2 equals k. So 2 minus 2 is going to give us n equals 0 to infinity. And in fact, it should be k equals 0. So that's going to be k equals 0 to infinity. C sub k plus 2. And then we're going to substitute x to the k plus 2. And then we're going to substitute for n, which is going to be k plus 2. And then we also are going to substitute for n right there. That's going to be k plus 2 minus 1. So that's going to be k plus 1. Right? And then finally, we just substitute back in for the last series. This one's easy because we just change all the n's to k's. So that's going to be minus 6 series, k equals 0 to infinity, c sub k, x to the k equals 0. All right, so let's play good news, bad news. Oh, and by the way, this should be x to just the k, not k plus 2. All right, so sorry about that. So that's part of the bad news. All right, but at least we found that. So let's play good news, bad news. So the good news is that we have x to the k, we have x to the k, we have x to the k. Everything looks okay except for the discrepancy between the indices. And remember, we need all of those indexes to be the exact same thing. And so how do we do that? Well, what we're going to do is we're going to split off k equals 0 and 1 from the second series. And we're going to split off k equals 0 and 1 from the third series. All right? The first series is going to stay the same. And remember, the trick is when you're splitting off terms, you always want to pick on the lower indices. All right? You can't really go backwards unless you do another change of variable. And at that point, it's just going to be too taxing. All right, so we're going to split off k equals 0 and 1 from, and I'm just going to do this. I'm going to call this asterisk and asterisk asterisk. All right, so we're just going to split off 4 terms essentially. All right, so let's plug in 0 and 1 into this second series. Now if I plug in 0, that's going to be c sub 2 x to the 0 times 2 times 1 plus, if I plug in 1, and that should be c sub 2, not c sub naught, sorry, plus c sub 3 when we plug in 1, x to the first power times 3 times 2. All right, so that takes care of this series. Now we're also going to plug in 1 and 0 into this animal. So it's going to become minus 6 c sub naught x naught minus 6 c1 x to the first. All right, so that's all the terms that we have to split off from the series, and now all the series begin at 2 now. So we're going to have series k equals 2 to infinity. c sub k, and then k minus 1, x to the k, plus series k equals 2 now, to infinity, c sub k plus 2, x to the k plus 2, k plus 1, and then finally minus 6 series, k equals 2 now, not 0, c sub k, x to the k, and that equals 0. Alright, so some more good news. We have x to the k in all of our series. We also have series k equals 2 to infinity in all of the series. So what we can do is we can factor that out, and simultaneously we're also going to simplify all of these constant expressions. All right, we'll see what to do with those in a moment. All right, so after just a little bit of algebra, we're going to get 2c2 plus 6x c3 minus 6c0 minus 6x c1. All right, so that's all of the simplified expressions for the constants. And then we're going to factor out the series k equals 2 to infinity, x to the k, all right, which eventually will be trivial. And what are we left with? Well, we're left with c sub k times k minus 1 and then we also have plus c sub k plus 2, and we have k plus 2, k plus 1. And then finally we just have this minus 6 ck. And all that equals 0. Alright, so let's do two things before we stop this part of the video. Alright, we notice that x to the k equals 0, which is true when x equals 0. And that's trivial. Alright, we don't really care about y equals 0. We already know y equals 0 is a solution. Who cares about that? We also know that 2c2 plus 6x c3 minus 6c0 minus 6x c1 has to be equal to 0. So we know that the sum of these terms has to be equal to 0. All right, because if it's not, then that doesn't make sense because we're adding those on to this series right here. And what we can do is we can just set up a system, all right, because it's 0 plus 0x. And so what we're going to do is we're going to set all the x terms equal to 0, and then we're going to set all of the constant terms equal to 0. So that's going to give us a system. 2c2 minus 6c0 equals 0, and then 6c3 minus 6c1 equals 0. Unlike the last examples, we're not going to get like c1 and c0 equals 0 or c2 equals 0 or anything like that. We're actually going to get c0 and c1 and c2 and c3 in terms of one another. All right, so what's going to happen is if we solve this for, let's just say c2, notice that c2 is going to be equal to 3c0. All right, just by adding 6c0 to the other side and dividing by 2. And then even better, c3 is equal to c1. So let's hold on to these. All right, they're going to be important. And then the last thing we're going to do in this video is we're going to get the generating function. All right, so we're just going to take all of this, and I'm going to copy it because we need all this. And what we can do is we can try to solve that for c sub k plus 2. So what I'm going to do is I'm going to add 6 c sub k. I'm going to subtract k minus 1 from both sides for the ck. So let's just do a little bit of algebra here. ck plus 2 times k plus 2, plus 1, excuse me, is equal to 6ck minus c sub k, k minus 1. Alright, so that looks pretty ugly, but let's divide both sides to solve for c sub k plus 2. And that's going to give us, in the denominator, k plus 2, k plus 1. Okay. I'm going to factor out a c sub k from the top. That's going to give us 6 minus, and then I'm going to distribute k to k minus 1. So that's going to be minus k squared. And we have a negative and a negative, so that's going to be a plus k. Just by doing a little bit of algebra there. Alright, so be careful with your signs, obviously, when we're doing this. Alright, we could factor out a negative k from everything right here. So if we do that, c sub k plus 2 is going to be equal to c sub k opposite, and if we factor out a negative, that just changes all the signs. K squared minus k minus 6 divided by k plus 2, k plus 1, and mercifully, this actually does get a little bit better. C sub k plus 2 is going to be equal to opposite c sub k. We can factor this trinomial as k plus 2, k minus 3, all over k plus 2, k plus 1. And now the k plus 2 simplify, and that's what we were hoping, that something would simplify. And so finally we get c sub k plus 2 is going to be equal to the opposite of c sub k, k minus 3 over k plus 1. Alright, so that's our generating function. And we're going to stop the video here, and then in the next video what we're going to do is we're going to use the method of iteration to be able to get to our two solutions for c sub n, and then ultimately get to two series solutions.